Okay, so we need to learn the grammar of bound. So we need to understand what to read in the matrix. Because I mean, perhaps you start on the fact that from the grammar of bound you have the variance and the lower bound on the variance, but you can read more. I intuitively gave you the concept of decoupling, and now we touch it more in a more rigorous way. So now the property that we have seen was that just to refresh, okay? So was that the variance of any estimator for a certain number of observation x, okay? And that one is, the variance is always larger or equal than the grammar of bound extracted, the element extracted in the AK position, which is obtained by the inverse of the Fisher information matrix on the parameter theta 0. Okay, so the grammar of bound depends on the value of the parameter. So you need to invert, and then you need to calculate the value as the K index. This K index is to recall you that it's a specific parameter. So for the frequency estimation, we avoided the K index by saying that we calculate the Fisher information matrix on the amplitude, we calculate amplitude phase, we calculate amplitude frequency, and so on. So we gave a name to the element of the Fisher information matrix, but in a general sense, this is what we can say. And because of the fact that the mean square error is variance plus a bias, and this means that if the bias is 0, that is the minimum we can get, and then the variance is larger than the grammar of bound. No, good. But this is the matrix. So what do we read from the matrix? Now, let's start from the shape of the error. So essentially, what we get is the following. Anytime we make an estimate, so we have a certain observation, but we make an estimate, okay? So we try to another set, and we make an estimate. We try another set, we make an estimate, that's proper, okay? So what comes out every time I make an experiment, okay? And if the estimator is unbiased, so these are the true values. Theta 1 and theta 2 is the true values, okay? So, and if the estimator is unbiased, that means that, every time I make an experiment, I get the estimate, theta 1 and theta 2. Then I may rerun the experiment, and then I have another estimate, theta 1 and theta 2. Then, I have an estimate, I have an estimate, I have an estimate, I have an estimate. Okay, so these are the, the samples of the estimate, the sample of the error. Actually, it's the estimated value. Okay, theta 1 hat and theta 2 hat. Okay, in this plane. So what I'm describing now is when I put many values, then I can draw, under the assumption that these the estimated value are zero bias, so there is no bias, so they are centered in the true value. That in addition to that, if we assume that these errors are Gaussian distributed, then we have this kind of shape of the bidimensional, in this case, Gaussian. So now this one is corresponding, okay, so this one is theta 1 hat, theta 2 hat. So if we repeat the experiments many times, and so our error is distributed as a, say as a Gaussian, if you like, okay? And so, given this Gaussian, I can find the area where, my experiment is collecting a certain set of values with a certain probability. So I can delimit the area where my sampled value, my sample estimate, are, constrained within a certain probability. So let's imagine that our probability is, X%, 95% or so. So that means that all the estimates are within these ellipses becomes ellipsis because it's a multidimensional Gaussian. So the joint probability is Gaussian, and then it comes to be, this ellipsis because I'm limiting, so I'm finding the ellipsis which is containing with a predefined probability all the samples, all the samples of the data. Now, so this is called ellipsis error ellipsis. Okay? So that means that this error ellipsis is a very nice abstraction to see what looks like the ensemble of the experiments, assuming that I'm making multiple independent experiments. So these experiments are clustering around here. They are distributed like that. And I don't know, with a predefined percentage, with a predefined probability, I have some estimates that are outside for that. Okay. Now, this means that my estimates are within these ellipses constrained to a certain probability. Now, so that means that my estimator now is represented by this distribution of the estimates that I'm doing. Assuming now that, to make it easy, assuming now that my estimator is ideal and it goes as a Kramer-Rao bound. So what I want to see what's happened if one parameter is known and if one parameter is not known. Now, so this is the distribution of the values. Okay. So this ellipsis represents the case where I'm not calculating, so I'm not constraining my set of parameters. So my two parameters are this. Now, assuming that the parameter, let's say θ2, is equal to the true one. So that means that the parameters are no longer two parameters but are one. So if I'm constraining the parameter θ2 to be equal to the true one, then I don't have two parameters but I have rather one. Now, so what does it mean? It means that if I constrain the true parameter, so the estimate is equal to θ2 because I'm not estimating this parameter because it's it's a true one. Okay? So just to simplify, assume that I have a sinusoid with amplitude, phase, and frequency, and I constrain the amplitude, which means I assume that the amplitude is known. Assume that the amplitude is equal to 1, and I know it. I'm not estimating that the amplitude. Okay, so I'm using my estimator not by estimating the amplitude, but by removing the dependency of the amplitude. So what does it mean here? It means that I'm cutting here because I'm constraining. I'm cutting my error ellipsis here. So since I'm cutting, my uncertainty on θ1 is this one, because my θ1, since θ2 should not be estimated because it's given. Okay. So if you assume that I have an amplitude and frequency of a sinusoid, and I use the known amplitude, then I need only to estimate the frequency because the amplitude is known. Okay. Then what means that my error ellipsis, since θ2 is fixed, is limited to this interval. So if I represent a distribution of θ2, θ1 in this case, which is now the only parameter to estimate is θ1, then my behavior is smaller because it's going between here and there. You can think about the error ellipsis as a plus minus 3 times standard deviation, if you like. Okay. So what's happened is that my dispersion of the estimated parameter goes here. But what's happened if I estimate θ1 and θ2 then? Well, if I look at from θ1 perspective, so I want to see what is the accuracy in θ1. Now, if I want to see what is the accuracy in θ1, then my accuracy goes from here to here. And so my degree of dispersion of the parameter, of the estimated parameter θ1, is going between that bigger interval. So, to conclude this story, if I estimate theta 1 and theta 2, my distribution of the estimate of theta 1 is going between this larger interval. And if I am estimating theta 1 given theta 2, which means I'm not estimating theta 2, then you know my dispersion is smaller. So, to conclude, now if I estimate, you know, if I constrain some of the parameters, then my dispersion is smaller, which means my variance is smaller. Okay? Now, this is the case when you know the two parameters, when the error ellipsis is oriented in this direction, so it's any direction, except with respect to the principal axis. Now, what's happened with respect when it's oriented as for the principal axis? So you can imagine that now it's oriented this way. Okay. Now, if the error ellipsis is oriented this way, so with respect to the principal axis of theta 1 and theta 2, then you know it doesn't matter if theta 2 is known or not. If theta 2 is known or not, the accuracy in estimating theta 1 is totally irrelevant. In this case, the two parameters are decoupled, because if I look at the covariance matrix in this second case, the covariance matrix does not contain a mixed term. And so the mixed term are the term in the covariance matrix which you know is defining the cross covariance between the covariance between theta 1 and theta 2. You know the covariance between theta 1 and theta 2 are set to 0 in the second case in the orange. So you know this is also the opposite one. So suppose that now I know the parameter theta 2. And now, I want to enrich my model and I want to estimate theta 2. Now, estimating or not theta 2 might be also saying that it's 0 or not. Now, let me make a very simple example. Assume that, because you did it, okay, and this is in your homework, so assume that, you have a filter, okay? And so, you have your system, and that's a filter, so you have, the input, a filter, the output, which contains some noise, okay? Now, this filter is HN. Now, for instance, we don't know exactly the length of the filter. And so, since we don't know the length of the filter, we are assuming that it's causal, which is not always the case, okay? So here I'm representing HN. Now, the true filter is this way, but I don't know the length. Okay? So I don't know how many parameters to estimate. And now what I can do is that, a very silly way to make it is, you know what? I estimate not just, 1, 2, 3, 4, 5, 6 parameters, but I estimate 7, 8, 9, 10. Okay? So when I estimate these parameters that truly are 0, okay, now what I do is that I am increasing the number of unknowns. Since I'm increasing the number of unknowns, I come out of that problem because I'm estimating more parameters than necessary. So if these parameters are decoupled with respect to the other, then that's fine. So increasing or not, it doesn't change. You see, it's still there. But neglecting the estimation of these 3 samples is equivalent to say that these 3, 4 samples are 0. So setting the samples to 0 means that you are estimating a lower number of parameters. So when I say here that theta 2 is known, theta 2 might be 0, for instance. Okay? So having a filter response that has some values that are 0, and you neglect to estimate those samples because you know or you assume that are 0, this means that you are using lower number of parameters to estimate the filter response. So now it's important to know what's happening if you estimate more parameters than necessary. And this is justified. So now, so going back to the point, if the Fisher information matrix, in general case, if the Fisher information matrix is behaving in this way, so that I can partition two sub-blocks of parameters, okay, such that the cross terms are 0 here, the off-diagonal terms are 0. Then we can say that the parameter corresponding to the group theta 1, which is theta 1 is indicated here, are decoupled from the parameter theta 2, which means that the group collected by theta 1 capital, so it's a multidimensional case now, okay, is decoupled from theta 2. Now, if, going back to this point, this example, if the 4 samples in the filter response are decoupled from the previous one, then it doesn't matter if I include or not, because it doesn't change. It does not degrade the variance of the previous one. But if the 4 samples are coupled with the previous one, I mean, it's dramatic, because what's happened is that every sample there needs to be estimated, and we know that this is 0, and so this sample will be estimated with a certain error, but this error is reflecting to the other true samples, and you degrade the estimation performance, the performance of the estimation. So now, if you have this structure and you manage to have this structure, as we did for frequency estimation, okay? You remember, amplitude was decoupled from frequency and phase, and frequency and phase are decoupled if I center the interval. Then in this case, the parameters are decoupled, and it doesn't matter if I estimate them or not. They are not mutually interacting. They are not degrading the performance of each other. Now, once more. What's happening if I have a nuisance? Well, sometimes, as we discussed, okay, we might have some nuisance parameter. Okay? So, like, I want to estimate the frequency, I have amplitude and phase as a nuisance parameter. Now, if the nuisance are not decoupled, so like in this case, imagine that, the nuisance parameter are theta 2. And theta 2 is grouping here. Theta 2 is grouping a set of parameters. Okay. So now what I do is I need to write the Fisher information matrix. But the Fisher information matrix here contains theta 1, fine. Here contains theta 2, 2. Okay. But the Fisher information matrix here contains theta 1 and theta 2. Remember, theta 1 and theta 2 is a group of parameters, okay? General sense. So, assuming now that these off-diagonal terms, okay, are not 0. So what's that? Now, if I calculate the Kramer-Rao bound, which is computing the inverse for that, when I calculate this inverse, now what's happened is the following: that if I go to the book, to the algebra, to the property of the algebra, I can see that inverting this matrix is equivalent to find the solution of the first block to be equal to this term, which is J11. Okay, J11, is the Fisher information matrix term that I'm interested in. Then I this minus J12, J22, minus 1, J21. Now, if J12 and J21 are different from 0, so I have J11 minus something. So a certain value J11, I remove something, but I calculate the inverse for that. So since I calculate the inverse of that term, this new Kramer-Rao bound, this Kramer-Rao bound here, is larger than the Kramer-Rao bound that I would have if I J12 or J21 is here. So, then I mean, it's what I get is that the Kramer-Rao bound is affected by the coupling effect. So this is how the coupling affect the Kramer-Rao bound. And if these parameters are nuisance, same story. If these parameters are nuisance, that having a nuisance is degrading the performance. And now, what could be the nuisance? The nuisance can be, as in the last time, can be estimating the phase. Now, why did I, since the phase is nuisance, why did I try to decouple the dependency of frequency from the dependency of phase? The way, the reason why I did this way is because if they are decoupled, then there is no interaction between amplitude and between phase and frequency, and then I can estimate the frequency with the same accuracy as if the phase is not present.
Professor, sorry, why do we have the stars in the matrix?
Which one?
Values,
The star? The star is other computation.
Any value?
No, it's, I repeated the computation on the star. Okay?
Okay.
So, I'm using, let me see. I'm using the inverse for block partition matrix. I will find it. I don't know. Okay, let me make it here. So, if I have a block partition matrix and I need to compute the inverse of a block partition matrix, here. This is the property I'm using. Which is in the book, page 5. So if I have A, B, C, and D, and this is the matrix, and each of these big matrices contains a matrix itself. Okay, this is a block partition. So if I need to calculate the inverse of this one, which is the same as there, okay, this is equal to another block partition matrix, which I indicated E, F, G, H. And E is equal to A is just minus B, A minus 1C. F is equal to blah, blah, blah. So, it's a rule which I apply. So when I put a star means, you can repeat the same computation for the others.
Okay.
So if you like, the one that could be of interest for us is J22. And by the way, since the topic is here is nuisance, so I'm not really of interest for me what is the impact of the nuisance parameter.
Okay.
Right. That's why I put the star. But in case you have a two group of parameters you have of interest, then what you get is, it's exactly specular. So I'm repeating, so let me copy here. So if they are of interest, then I'm applying the formula and the variance of theta to half is larger or equal than so it is J22 minus J21, J11 and then minus 1, J12, everything to the minus 1. So it comes out at, again, you know, the off-diagonal term, the presence of these off-diagonal terms are, you know, degrading the performance. And clear?
In a Fisher information matrix, the element of interest is always J11?
No,
It changes.
it depends where you put it. I mean, you can put amplitude, phase, frequency like we did.
Okay.
And then, you know, it depends on where you order. Very important that you keep the order. I mean, so if you started to say amplitude, frequency, and phase, you need to continue to use that order.
Okay.
Don't mess up. It's easy for 3 parameters, but you know, when you have many parameters, sometimes you manipulate and then you might implicitly, I mean, unconsciously, permute the order and it becomes a mess, okay? So be very attentive. I would say there is another comment that I don't find here, so that I might introduce and have now, which is can I have an approximate formula for, you know, for camera bound? Sometimes I'm in such a mess here. Sometimes, you know, I mean, the formula says the following. The formula says that, you know, the variance of theta k is larger or equal than j minus 1, calculating in the true value of theta, and then you extract, you get the parameter k. Okay. Now, if you think about, you know, the concept of error ellipses, then what we get is, I mean, of course, considering 2 parameters, what we get is the following. So, you know, my error ellipses, this is the parameter theta 1 hat, and this is parameter 2 hat, okay? And so, you know, when I look at the parameter theta 1, let's put the theta 1 here. Let's make the case on theta 1. So that means that I need to compute the inverse and then get, you know, the parameter theta 1. Now that means that the degree of uncertainty goes from here to there. Okay. So then this is approximately the visual representation of the j minus 1, 1. Now, you know, I can also look at that calculating the camera bound implies that I need to calculate all the Fisher information matrix elements. Because, you know, if I want to calculate the camera bound for frequency, I need to calculate the derivative as we did, the partial derivative with respect to the amplitude, partial derivative with respect to the frequency, partial derivative with respect to the phase. We need to calculate the partial derivative for all the entries. If the number of parameters is easy, like the 3 parameters, that's okay. But if the number of parameters are very big, then, you know, it might be very annoying. Huh? Now, if you are not lucky that the parameters are decoupled, then, you know, a very nice trick that you can calculate is the following. You can imagine that the other parameters are known, and then you calculate this as a bound. Now this bound, which is simply, this is J11 to the 1 over J11. So, you know, calculating this distribution means I'm assuming that theta 2 or the other parameter are not there. Now, if I use the property of the algebra, I know that this let me say, this bound is not that tight, and essentially this bound is, if you like, is J Fisher computed in the entry 1, which means I'm extracting the entry 1. So, you know, this is not a Kramerov bound, this is an approximation. Is lower than that. Okay? So that means that, you know, if we make our practical case, if the Kramerov bound goes here, this is, for instance, a sealed noise ratio or number of samples, whatever. Now, this new bound goes there. This is by computing J11 over. Essentially, we are not inverting the matrix. Okay? So don't make a mistake. The bound, you know, has to be on the, upper than that. So my mean square error should be larger than that.
So if it's decoupled, the equality
They are
holds.
equal. If the problem is such that the two parameters are decoupled, you know, they are equal. If they are not decoupled, that is lower, okay? So that means that any experiment, okay, you know, if we have an estimator that is efficient, okay, it goes like this. We don't know where is the Kramerov, you know, and we can find this gap. But this gap is not really a gap. It's a gap of our approximation using this bound, this approximate bound. And that's it. For non-Gaussian, you know, it's for the other course. Okay. I don't think there is one property. Let me add another page. It's not in the slide, but you know I had it here. Sometimes, you know, you might get that you need to calculate the Kramerov bound for a transformational variables. So imagine that, you know, I have a parameter and we call it theta enough, okay? So imagine, you know, I have alpha equal gamma time theta. And assume that I know the variance of theta. Okay? So now if it is linear, that's trivial. Because if I want to get the variance of alpha, that is equal to gamma squared, the variance of theta. Okay? If linear. If I have a linear relationship. Easy, trivial. Now, let's make a little bit more complicated. So let's assume that now alpha is a function of theta. And the function is arbitrary and non-linear. So that means that, you know, what we need to calculate is how can I map the variance of alpha on the variance of theta? Now, for instance, theta, you know, on theta I can calculate the variance, or can calculate the Kramerov. And then I can map the variance from theta to the variance of another variable. Imagine that I take the frequency and then I calculate the square of the frequency, and then I want to calculate what is the variance on the square of the frequency. How to do it? So, I mean, making is very easy. Now think about what does it mean transforming. Transforming means that I have, you know, a mapping between theta and alpha. Alpha is another representation. Now, so that means that my function, this is the g of theta function. And then, you know, let's assume that this variance is calculated with respect to the two parameters, theta and theta. So let's assume now, this is one dimensional, okay? So let's assume that, you know, I have a certain dispersion of this Gaussian. So how to map this dispersion onto the dispersion of alpha? Now, first of all, this alpha 0, you know, is the mapping between theta 0 and alpha 0 according to the transformation of G. So, I mean, the easy way, the most intuitive way is the following. I take the transformation, I make the linear approximation, okay, and then, you know, I can, by this way, I can transform, you know, my non-linear transformation into a linear one. Now, this holds true, which means this is valid when the variance is very small, or when the transformation G is not very crazy. Okay, so if G is very smooth, like the square root of, I don't know, something similar, that's fine. If the transformation is a cosine, you need to be very careful, because you know the cosine, it makes sense if you are in a neighbor, or sine, you are in a neighboring of the transition between, I don't know, the +1 and -1. Okay. So now let's write what we did. Okay. So that means that, you know, in case I have an estimate, so my estimate alpha n is equal to G of theta n. But, you know, this can be written as approximately as G theta 0 plus the derivative of G function with respect to theta computed on theta equal theta 0. And then I have theta hat minus theta 0. So this is the series of the any possible value. Take this as theta hat and see where is it mapping there. Now let's compute, you know, the variance. Now the variance is very easy, okay? Because what comes out is that this is alpha 0, and so I have alpha hat minus alpha 0 is equal to derivative with respect of G with respect to theta computed on theta equal theta 0, and then I have a theta hat minus theta 0. So if I need to compute the variance becomes variance of alpha is equal to the derivative of G with respect to theta, and theta equal theta 0 square, then variance on theta. Okay. Now this relationship can be generalized to the multidimensional case, and you can find them. So now don't tell me that you don't know how, in case you have a variance, you don't know how to manipulate the variance. Because this is the very easy way. Now, where we use it? We will use it for the following problem. There is a class of problems that are called the directional arrival estimation. Now, we will see that in the directional arrival estimation in array processing, you remember, directional arrival is when I play with the Wii. And the Wii is, you know, is localizing where I'm holding the tennis stick, okay? Actually, the tennis stick is not really a tennis stick, but the tennis stick is transmitting a signal. The array has a set of receivers, and the set of receivers are measuring the position in space where the tennis stick is, okay? So we will see that the problem of estimating the angle, the directional arrival, the angle of arrival, so the angle where the wavefront is impinging into the array, which comes from the tennis stick. Okay, you see? Have you seen Wii? You know the Wii. What is that? A game? Okay. Yeah. So if you don't, you know, go search on Google and then you will find it. And then so you get the positions, the angle of arrival. So this problem, which seems totally different from the frequency estimation, we will see that it's exactly the same problem, except that there is a transformation between frequency and the directional arrivals, and the transformation is a nonlinear function, which is specifically is a sine function. Sine, okay? So, you know, that means that this nonlinear transformation to get the performance of another problem, once we compute it with the previous one, is something that will be useful. So once we know the Cramer-Hall bound for frequency, we can map this problem into the Cramer-Hall bound for directional arrivals by simply making the transformation, the mapping. Okay? We will, you know, we will see that. We saw it. This is the example. Yeah. No. Read it. I don't want to spend time. Okay. This is for advance. We didn't do the camera for continuous time. I now remember. Anyway, so in case of the efficient information matrix for continuous time, I was convinced that we did. In the efficient information matrix for continuous time signal, it's simply I take the formula and I calculate that. Okay? So I take the formula, I calculate, blah blah blah, here is the blah blah blah. Okay, blah blah blah, you know, it comes out that the efficient information matrix elements are computed in this way. So it depends on the derivative of the signal depending on the parameter with respect to the specific parameters. Now, we look at this specific case and we make an example of that. Okay. So, let's write it here so it's in front of us and when we make the example. So for efficient information for continuous time, and I have a J is equal to 2 divided by n0, which is the power spectral density of the noise, integral from 0 to t, the derivative of the signal model depending on the parameter theta with respect to theta I, the derivative of s with respect to theta dt. Okay, I simply copy that. Okay, so that's, you know, this is the one that we're going to use now. So let's use it. Let's calculate. Let's make an example. Oh, here is the exercise. Now, you did with Matera, you know, the computational time of delay. So I'm not touching that, okay? But I calculated the camera out. So the example of the time of delay estimation, this is to do, is the case where, you know, you have an echo. So your data is composed by a waveform, okay, and this is the waveform delay by tau, and the amplitude is capital A. And you know, in the data, this waveform, delayed waveform, is affected by noise. So, you know, what I usually do is that I try to window my observation, my data, such that my observation fully contain the waveform. Now, let's fix this aspect. Why am I saying that, you know, my interval 0t should fully contain the waveform? So that means that the delay tau should be internal to the interval 0 capital T. Now, if this is not the case, then I have some truncation effect. So imagine, just to be more specific, imagine that the waveform, so should be fully contained in 0 t. Now, let's make a counter example of that. Imagine that my interval 0 t is this one, and my waveform, let's make a triangle as a waveform, just to make it easy, okay? So my waveform g of t is a triangle minus dg, and the amplitude is 1, okay? Just to make it easy. Now, so, if the delay is very big, then, my waveform goes like this. So the delay is tau is 0. So what's happened? What I measure here, I measure the noise plus the tail of the data. This is something that does not exist. I'm not measuring that. So, this is a very simple example. Let's make another one. Assume now that, I measure this way. Let's make it here. So tau is 0. Now, in both cases, the waveform is not fully contained into capital T interval, because there is just a tail, a piece of the waveform. And so, what I do is I'm assuming that the waveform is fully contained, which means it's completely included into the 0 capital T. If it is not included, that means that, it looks like if there is a missing part. And having this missing part, okay, this missing part of the waveform is as a consequence of destroying the performance of any estimator. Because it's simply, the estimator expects a triangle. You give as a data something that is a piece of triangle. It's like if you expect to see a person and you see just a piece of a person. You don't know what to do, right? Yeah. So, when you estimate something, you are setting a model where the model should be made in such a way that it is a representative of the experiment. So, this is the reason why the waveform should be fully contained. Okay? So fully contained means here, 0 capital T, so blah 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 blah, 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 like that. Okay? So okay, no. Is it clear? So that you can visualize what is a good experiment, what is a bad experiment. In practice, what you do is just shift the observation window such that you fully contain the waveform. Now, so this is the sentence, assuming that the delay is such that the waveform is fully contained into the observation window, which is the observation window is 0 capital T. Let's go to the point. Now, so in this case, we can write the log-Lacture function. And for a continuous time, we know how to write it here. Okay? And we can maximize the log-Lacture function. Fine. Now let's assume that in this example, A and tau are parameters. So we are in an experiment where amplitude and delay are both parameters. We don't know if amplitude and delay are coupled or decoupled. They are both are parameters. Okay? And I leave it to you to calculate, the maximum likelihood method for amplitude known. Now, so that means that I need to compute, I need to optimize this function with respect to amplitude and delay. Now, amplitude is linear. Delay is hidden into the waveform. So what I do is I solve the quadratic part, which is the linear part. Now, when I solve it, so that means when I write all the terms, okay, so I have this here, this one is the energy of x. I have integral of 0 t, xt, gt minus tau. Tau is the unknown, and a is the unknown. And here I have an a square, and then I have tau. Now, if the waveform is fully contained, if the delayed waveform is fully contained into the observation window, this term, this one, is not dependent on tau. Because no, that is the energy of the waveform delayed by tau. But you know, since I'm considering that the waveform, the delayed waveform is fully contained into the capital T interval, then this term is not dependent on tau. So this, specifically, this term is energy of the waveform G. So this is the first term is the energy of Gx, this is the energy of G, and then you know, I have the cross correlation between x and G. Now I'm solving with respect to A here. When I solve it, what I do is, so the solution is it's quite easy because I mean the solution is the cross correlation divided by the energy of the waveform. Sometimes called normalized cross correlation. So you know it's the cross correlation of the data, the signal with respect to the waveform. And you know, I am assuming that I know the delay. So that means that you know this amplitude is dependent on tau. So what I do now, I take this formulation and I put it here and there. Okay, putting that one here and there, and then you know, that means that what comes out is a Laplace function which is not depending on the amplitude but just on the delay. And, you know, and the Laplace function is the energy of x, which is not dependent, you know, is the energy of the signal, it's not depending on tau. And the second term, which is the square of the cross correlation, and that one is depending on. So I search for the square of the value. I search for the value of the delay that is maximizing the square of the cross correlation between the data and the delayed waveform. Recall that the denominator is the energy. Okay, all these sentences discussing about if the waveform is fully concatenated, blah blah blah. Okay. Good. Now, you can repeat the same exercise, same example, okay, by assuming that the amplitude is fixed and is known. That means that you don't need to optimize with respect to the amplitude, but you simply need to optimize with respect to the delay. You will see that the result is very similar, not exactly the same. Now, there is not this square. It is the maximum of cross correlation if we know the amplitude. If you don't know the amplitude, it is the maximum of the square of cross correlation. Okay? Prove yourself. Let me write. Prove the NLE for known amplitude. Okay? Make it by yourself. I think it was in one of the exams. Now, okay, fine. Now let's calculate the Kramer-Rao bound. So in order to compute the Kramer-Rao bound, this is what I wanted to do as an exercise today. So if I need to calculate the Kramer-Hall bound, you know, using the formula which is written here, I need to isolate, you know, the dependency on the model. So the dependency on the model in this case is my model, so ST, depending on the parameter theta, okay, is equal to A G T minus tau. And the parameter theta are amplitude and tau. Oh, let me see if I order amplitude tau or tau and amplitude. Amplitude tau. Good. Okay. So this is, you know, what we need to calculate. Now let's apply the formula. Let's read the formula and apply it. So what is necessary to apply the formula is the following. I need to calculate partial derivative of A G T minus tau with respect to one of the parameters at the time. So I have amplitude. And I need to calculate the other, which is the partial derivative with respect to tau of A G T minus tau. Okay? This is what is required, right? If I see that. Okay? So, I don't know. So that means that, you know, looking at the Fisher, so let me write completely the Fisher. So I have a Fisher J A, I have a Fisher J A tau, I have a Fisher J A tau is symmetric, and then a Fisher J tau. Okay. So if I need to compute the JAA, I start with the first one, JAA. Okay, then I need to calculate 2 over 0, integral 0 t, and then it is the derivative with respect to the amplitude of that one, which is A G T minus tau multiplied by itself, squared dt. Okay, reading that. So, you know, what is the derivative with respect to A? Is G of T minus tau. So this derivative is equal to G of T minus tau. So what is the derivative here? It is equal to, so it's a derivative with respect to tau. So amplitude is a scaling factor. So I have, it's a derivative G prime of T minus tau. Then is the derivative of minus tau. So it's minus that. Okay? So, you know, this one, I start with this, okay? So this one is the derivative with respect to A of that one is G of T minus tau. So, you know, continuing is T2 divided by N0, integral of G of T minus tau squared dt. So, which is, this is the energy. Okay? So it is 2 times N0 multiplied by the energy of G. Okay? Let's do the other. Let's do the other. You remember that. Let me see if I have it there. No. Okay. Let me copy here. So all these relationship depends on the derivative with respect to A of AG of T minus tau, which is G of T minus tau, and the derivative of with respect to tau of AG T minus tau, which is equal to minus G prime T minus tau. G prime is the derivative of the waveform. Okay? So we will see now. Okay, so these two relationships I copy there. Let's calculate the second one. So, I mean, I calculate amplitude and delay. So it's 2 times 0. Then it is derivative of, with respect to the amplitude, which is gt minus tau. And then I have the derivative with respect to tau, which is a. Where is a? Forgot. Okay. Which is minus a g prime t minus dt, which is equal to minus 2 times 2a divided by 0 integral of gt minus tau g prime t minus tau dt, which is what is written there. Okay. Now, why that one? You know, when I compute it, why this one is 0? Now, first of all, you know, since the interval is larger than the waveform is fully contained into the interval, okay, then, you know, it's all the same to compute integral of gt g prime t. It's the same. Because, you know, it's not, I mean, the interval is 0, capital T. And, you know, so we have our interval that is 0, capital T, and you know the delay is any place. So here I have the product of the waveform and its derivative. But you know, I mean, this quantity is not dependent on tau. And so since it's not dependent on tau, I can choose any arbitrary value of tau. And so, given the arbitrarity of the tau that I choose, I prefer to choose tau equals 0 for this case. It's like here. When I say that the square g square t minus tau is equal to the energy, what am I saying? That, you know, since the interval capital T is so large that there is a waveform here in the center, it's limited there. Then, you know, I mean, in order to compute the integral, I can put this waveform wherever I want, provided that when I compute this square, I'm computing the square for all the waveform. I'm computing this, you know, this integral using all the waveform. Then, given the arbitrarity, I can set the tau equals 0. Okay? So this is the reason why, you know, from the upper part, so from the upper part here where I have a t minus tau, on the lower part I have a g prime t. Actually, technically, I hope I didn't see the book already. Mistake. I need to correct the book. When I write this interval, you know, the stream is all the support of the waveform. So it's not 0 t. Because I mean, if my delay is going from 0, then, you know, I'm missing one part of the waveform. My waveform is a triangle, and I calculate everything from 0 to t. You know, I'm skipping that part. Okay? Is it clear what is the mistake? No, I need to correct. So all these intervals is for a large enough interval of computation. Now, okay. So this one is equal to 0. And there is many ways to derive that g times g prime integrated is equal to 0. Very simple way. Let me make a star. Now, when I compute the integral of g of t, g prime of t, dt, I need to remember that if I calculate the integral of the odd function with an even function, the integral is 0. Odd function, know what is odd? Okay? Odd function and even function. Okay? So if I calculate the integral of an odd function, then that is 0. If I calculate the integral of a product between odd function and even function, it's it's odd and is 0. Now, so let's see. If g of t is even function, g prime of t is odd. And then I compute the integral between an even function and an odd function. And that is equal to 0. Now, this is more general. You can exercise yourself. You know that if I have a g that is arbitrary, I can divide g into a g even plus a g odd. And then when I compute the derivative of g prime, then I compute the derivative of g prime even plus g prime odd. And when I compute the integral, then I have g even prime, which is odd. I have a g odd prime, which is odd. Then I have a g odd prime, but I have also g odd, g even prime. So because of that, the integral is 0. Now, if you don't like this proof, but you are very familiar with this is by using the simple calculus, analysis 1, 0, high school, okay. Now, if you don't like this rule and then you prefer the Fourier transform, then you can use a Parseval, and then looking at Parseval, this is equal to integral of g omega, and then I have j omega, g omega star d omega, okay, by Parseval. Then this is equal to integral of j omega, and then I have a g omega square d omega. But g omega square is even, and omega is odd. And this integral is equal to 0. So this is the more evolved way by using the Fourier transform, and this is the high school way. Okay? As you wish, choose the line. Anyway, so out of any question that JID or IID, here I use I, so the cross terms are 0. So that means that amplitude and delay are decoupled. So blah blah blah, this is equal to 0. So when I plug the pieces, this is equal to 0. This is equal to 0. This is equal to, where is it? 2 times n0 divided by EG. And then I have only that one, which is different from 0. J tau. So if I'm interested to calculate the variance on the delay estimation, then it's enough that I get this one. I don't need to calculate the other. In other words, the variance on the delay estimation is the same even if I know the amplitude. It doesn't change because the two parameters are decoupled. So I'm using the property that we derived 1 hour ago, 40 minutes ago. So, the variance or the Cramer-Hall bound, so the variance on the tau, okay, is largely equal than 1 over j tau tau. Here I use I tau tau, so it's only because in the numerator I put j. Okay, anyways, so it's equal to that, and since tau and A are decoupled, okay, even if the method, so the maximum likely method to estimate the delay, if the amplitude is known, which is just a cross correlation, the value of the maximum cross correlation, or the amplitude is not known, which is the value of the maximum of the square of the autocorrelation, of the cross correlation. So the methods are different depending on if I know amplitude or not. So since they are decoupled, the variance is independent, it's decoupled from the amplitude. It's not dependent. The two results comes to be the same. Okay? Important property. Important mostly for the radar people. They like it. They like this property because the amplitude is describing the scattering property of the object. And the delay is describing the position. Okay? The amplitude is describing, it depends on the size of the object. If I'm a policeman, and I'm pointing with the device, and and the size is defining the amplitude. And the delay, since it's decoupled, then the delay is decoupled from that. The delay is defining what is the distance from the object. Now, so concluding, okay. So when I apply now the property of on the tau tau, that is equal to 2 times a squared 0 divided by n 0, and then integral g prime. I can compute this way. Now, rather than computing as integral of the first order derivative, I can compute in the frequency transform. I use it possible as well, because it's a square. Okay, since it's a square, it's an energy, then I can apply possible. So when I have the derivative of the signal in time is j omega in frequency, and then the possible. Here, this formula guarantees that I can calculate, the j tau tau. Now, which one to use is a matter of preference. You can either use this one, or you can either use the other. Now, when I substitute the pieces, blah blah blah, and they keep on moving into the exercise, then it comes out that the variance is larger or equal. By the way, this is by computing just the 1 over j over I tau. So that is the inverse, that's because it's decoupled. Then it comes out that the Kramer-Rao bound depends on the energy of the waveform, N0, the power spectral density of the noise. Usually this is called signal to noise ratio. So it depends on 1 over the signal to noise ratio. It depends on something else. It depends on 2 times beta g, and then the amplitude. Yeah, of course, the bigger is the amplitude, and the more is the energy of the signal that I get. So it's not that surprising. So if my reflecting object in the story of detecting the distance of the car that is running at 190 kilometers per hour, okay, in a city, which is, it's forbidden, and then, this depends on the amplitude. So it's bigger, I get a bigger amplitude. Now, what is this beta g? This beta g is called effective bandwidth. Now, this effective bandwidth, okay, is, look at here, is omega squared, g squared omega. G omega is the Fourier transform of g of t. So that one is the Fourier transform of g of t. So this one is overall is absolute square. Okay? then multiply by omega squared. Now, from this, and the denominator is the energy. Now, if I put it this way, so this one is, why is effective bandwidth? You know, because I can reverse the formula. Let me show you here. Let me make it again. Yeah, I make it. Now, if I reverse the formula, I can write it this way. So I have integral of omega squared, absolute value of g omega squared d omega. This is equal to beta g squared integral of absolute value g omega squared d omega. So this means that, you know, if I have a waveform, this is the Fourier transform of the waveform, g omega. Huh? So if I have a certain waveform, g of t, that is low pass as a characteristic, very much low pass. Okay? So this means that in omega, you know, this contains a lot of low frequencies. Now, okay, so I'm computing essentially. This one is computing the body center of the frequency. So the higher frequency counts more than the lower frequency for accuracy. So if I consider this waveform and this Fourier transform, or I consider another one where for the same energy, but you know the spectrum is distributed, so the Fourier transform is distributed like that. In the second case, that is omega. In the second case, since I have a dominance of high frequency, this high frequency, when I compute integral of omega squared multiplied by the square for that, okay, the high frequency are making the effective bandwidth very large. Keep in mind, this is the energy. So if I make an hypothetical exercise such that, you know, I choose the two waveforms to have the same energy. Energy means same area. Okay, this is the energy. So if I constrain, you know, the two waveforms to have the same energy, the one on the right, since when I integrate, you know, the high frequency counts more, then the second one on the right has a higher effective, effective bandwidth, and then, you know, since the beta is bigger, look at there, the beta goes as a denominator, so 1 over beta is smaller. That means that the variance is smaller. That means that it is more accurate. So for the same energy, I can choose the waveform such that the distribution of the energy over the frequency band is unbalanced, preferably to the high frequency rather than to the lower frequency. Okay. It's important, that one, because, you know, you can study the waveform. So given the energy, and you know, you can choose, for instance, you can choose two waveforms, like this one and that one. And, you know, and the spectrum allocation is the same, and this is an absolute value of g squared, and this is absolute value of g squared. The energy is the same. Now, this is the case A, this is the case B. So, resolution, accuracy. For GA is lower than GB. Assuming hypothetically, you know, that I can make this experiment. Remember, same maximum frequency. So that means that this is a degrees of freedom that I can use it in designing the waveform such that the waveform enables the maximum possible resolution. Now, since I have no time to make the double delay, but let's do together, okay? One simple case. So, assume that, because this is, this is taken from one of the many examples. Huh? So everything depends on g of t, on the shape of g of t, or the corresponding frequency content of g omega. Okay. So assume that I give you this problem. Given blah blah blah, estimate the delay of a system, blah blah blah, and then I ask you to calculate the camera bound for g of t equal to a triangle. Okay, and this g of t is a triangle, and it's going between minus tg and tg, and the amplitude is 1. So let's calculate, the camera bound in this case. Now let's start to compute the energy. What is the energy of G? What is the energy of G of t? Energy, integral G of t squared dt. You know? Can you say something? Would you say 2tg times 1 divided by 2? Square. Okay. Good. Very good, guys. So, this behavior, so I look at one side because the other is the same. Okay, say it is 2 times integral between 0 and tg of what? Of 1 minus t divided by tg, because this is the behavior of a line. Okay, because when t is equal to 0 is equal to 1, and when t is equal to tg, then this one is equal to 0. Square dt. Okay, that's the energy. And so, now let me see. Okay, now 0 to tg, then it is 1 minus 2 t tg plus t squared tg squared dt. If you don't remember the integrals, it's better to change the job. So, and that one is tg. Then I have a minus, now this one, which is 2 makes 4. Then I have a tg here. And then it's t squared divided by 2. So it's t squared divided by 2 calculated from 0 to tg. And then the last one is plus 2 tg squared. And then it is t squared is t cubic divided by 3 computed from 0 to tg. Okay. So minus 2 times tg, this is 2, nothing. Okay, now this one is tg, the other is 2 times tg squared divided by tg, so 2 times tg minus 2 tg, because of tg squared divided by tg, plus 2/3 tg squared tg cubic, so tg. So it is 2/3 tg. Okay, so that's the energy. Okay, so the energy, I go here, I put it here. Ag is equal to 2/3 dg. Now I calculate the first entry in the camera album. Is it clear? Nothing, okay? Just completely the integral. I could have done before, I mean, this was easy. Now, let's compute the other part. So the other part, you know, when I look at the formula up there, so it is 2 divided by 2a squared divided by n0. So tau is 2 divided by a squared divided by n0. And then it is the integral of g prime. So what is the integral of g prime? Now, what is the integral here? So the integral of the derivative. What is the derivative here? Now, the derivative we know is 1 dg, right? And then you know it's constant here, positive, and so 0 here, constant, negative, constant, and 0. This is g prime. And the value is this divided by tg, okay? So it is 1 over tg is the derivative.
Isn't that the squared derivative?
Okay. So it's 1 over tg for that, okay? So you know what I need to compute the square for that. So the square is simply from minus tg to dg is 1 over tg squared. This is g prime t squared. So I'm calculating the integral for that, which means that it is equal to 2 times tg divided by tg squared. So this is equal to 2a squared divided by n0. And then you know let's secure this integral, which is 2 times tg divided by tg squared. Now you know what I so which is equal to 4a squared divided by n0 divided by tg. But you know, tg, I prefer to write tg as the energy. I prefer to write that way because it's meaningful. And then you know, tg, so write it this way, tg is equal to 3eg divided by 2. So I plug into there. And that is equal to 4a squared divided by 0. And then tg is equal to 3 eg divided by 2, which is equal to 8 divided by 3 a squared something wrong. Something wrong. I need to, sorry, it's late. I need to see. And now I can see it, you know, correct. Okay, but you know, there's something wrong because I mean, comes the energy and it put it together with the n0, okay, which makes no sense. So the other possibility is that since you know the energy has these special behavior, Okay, so when four A squared. And then I plug here the energy. So to write in a conventional way is 4A squared 3 divided by 2 EG, and then it is N0 multiplied by PEG squared. Now, this one makes more sense for me. It's the same formula. The reason why there is this mismatch is because I choose the amplitude to be 1. So since I choose the amplitude to be 1, the energy becomes the time, which is, dimensionality doesn't come out. Okay? So if I choose, if I, that will be more serious. If I choose the amplitude to be A, and I repeat my computation with the amplitude to be A, then, this mismatch with the dimensionality does not appear. That's way too